Hello, everybody. Welcome to my talk on generalized decoupled shading for EGSR 2022. So let me start with explaining what decoupled rendering is. There are a lot of terms that go around the industry. So some people call this texture space rendering, some people call it object space rendering. I've called it that in the past. Um, but we like to call it decoupled rendering because that's sort of the superset explanation. And the idea here is that your shading is just decoupled. It's different from the screen sampling. And it may be different in, not just spatially but temporally. So the broad term that we've come up with is decoupled. You're not shading in the space of the screen. This is a similar concept to raise. So the idea of shading before you rasterize or render is something that came from them. It's one of the inspirations we had for trying to do this. And there are a lot of advantages for this that are well known. Shader anti-aliasing is a great one. BRDF stability, a lot of the models just become more stable when you're shading this way because you can filter them after the inputs. There's a lot of temporal stability. You don't get a lot of the shimmering frame to frame because you're always evaluating the same sample. So it might be wrong, but you're wrong the same way. And so you got a lot more cohesion. In fact, we find that we don't need to do temporal anti-aliasing. It's just not necessary for our engine. But the real kind of question here is, there's a lot of advantages, not a whole lot of disadvantages in the terms of graphic fidelity, but no one's built it in a general way. There's not a solution that you can say, I'm going to build a render and it's going to work and it's going to be decoupled and it'll work in like any type of game I'm going to make. We did this and some rendering in Ash with the Singularity, but it was a very rudimentary system. I'll talk about that in a second. And there was some mega texturing from Doom that might have been a path here, but that ended up dying. I'll talk a little bit about from what I know. I'm not an expert at that, but from what I know about why that didn't work out. I want to point out that this paper is not an evaluation of the differences between decoupled and other rendering techniques. I think that's a great subject. I think that somebody could do an exhaustive research and it'd be an entire paper, a series of papers just exploring the differences between them, and they are substantial for terms of quality. But this is not a paper about that. This is a paper about implementing decoupled and saying how can you make a decoupled render that will work in a real world setting. So yes, that's the point of the paper. So why haven't we made an obstacle? Why haven't we made a decoupled render? What obstacles exist? So why don't these exist in the marketplace? There's a whole bunch of reasons. The art assets can end up needing a different process, which is a major issue. Trying to make a big game, assets cost a lot of money, and if you have a different technique than what's commonly done or more expensive, you just may not be able to get it done at all, even for any price. So that's a problem. So there's a lot of work you have to do to try and just use existing pipelines. I put in bold the biggest one, which is just that there's too much memory needed. And this was cited for a reason in megatextures, too many samples. Which related to the other thing is that the performance overhead might be too high because you might be shading too many things, which is related to memory things, which is also related to the fact that the visibility just wasn't fine-grained enough. So this is just exasperating. We're shading too much stuff. We're trying to shade too many things are visible. We weren't able to determine the particular shade visibility that was visible and things that weren't, and that basically meant that we couldn't deal with it. We didn't have very good performance characteristics. And then finally, there's some engineering, just building a material integration system. Like we have to be able to material things. We need a material system that will work at production level with tech artists. So we need something people can use. So people are used to writing vertex shaders, pixel shaders. We have to have some way that's roughly analogous or equivalent to them, be able to make materials for it. So let me talk a little bit about prior methods. There's not a whole lot of stuff here because not a whole lot of stuff that shipped, but we did ship Ash to the Singularity over 5 years ago. And this was actually a fairly straightforward solution. We rendered every object into its own section of a texture, and we did this based on some CPU metrics estimating how big an object would be. Now this kind of worked because we knew that we didn't have a whole lot of overdraw, and we also knew that objects weren't spanning so much space on the screen that the texture density was varying. This wasn't true for terrain, so we had our own custom solution for terrain, which a lot of people do. That was very, bespoke to that system. But in general, we just sort of made it work because we knew that we had the constraint a game that allowed us to experiment with it. And we learned a whole lot about it, but it certainly wasn't a general solution. A common complaint I got, or comment rather, about our presentation was, oh, that's a great technique, it's a cool idea, but it's not going to work for my game. No, right, it wasn't going to work for any game. Because it wasn't a general solution, it was a specific solution. We also built, some people saw it, it wasn't widely circulated, this demo called Not Enough Bullets, which is a VR demo. This is similar to some other techniques people had done at the time. The idea here is we broke the scene up into an objects up into little tiny chunks, and then we did the visibility checks in each little chunk, and then we could range each chunk. So it's sort of like an extension of ashes, where by break an object into sub objects to try and allocate them, and it's roughly somewhat how you might have done mega texturing. There are a whole bunch of problems with this. The biggest one was just there's too much, still way too much memory and way too many samples. Like even when you did this, it was just too much. And the other problem is it was hard to make the art. It was just difficult. And we did think that we could, even if we could get some of the other techniques working, we didn't think we could afford to produce art at that scale. Like it was just, you can't make art more expensive to make it perform well. There's also other problems too. One of the problems is like you ended up with obvious seams between the different detail transitions, which you don't want. You want a nice smooth blend. You don't want like see a seam or texture density changes. So there are some problems on that caused a lot of issues. But there were some neat things I won't talk about too much, but we experimented with shading at lower rate and delaying, and all this stuff is quite fruitful and seemed to work quite well. But we don't do that in our current technique, and I'll explain why at the end. So the question is like, so what was our solution here? So what we're trying to solve was we wanted a general system, a system that would just work pretty much as well as any forward or deferred render. Like if you had a scene that was, we're going to render fine with deferred or forward, it should render fine with us, and shouldn't have to think about it too much. And the idea here is that we were going to use advanced DX12 features to compute the visibility to really fine grain, because everything came down to that visibility. Like we couldn't be shading things that weren't visible, and we need to be able to blend between things that were visible. And those were the big things. So we're going to leave the CPU out, and that's not completely true, but it's mostly left out of trying to figure this out. And it's all done at a very precise level in the GPU because GPUs are quite programmable to figure this out. And then we're going to virtualize the shader storage space so that we weren't even backing things that weren't visible. So we're only going to physically back things that we knew are visible. So not only were we going to get a very precise estimation of what was visible, we weren't even going to bother storing shadal samples. I'll talk about shadals in a second. For things that weren't visible. And there's some asset processing that's in the paper that's important that just let you work with other assets. And then we built a custom material language, talked about a bit, to build a virtual material stage. So we have our own language, which has our own virtualized material shader stage, which enables a lot of programmability and hides a lot of things to make it productive for artists to use. So I talked about shadal a second ago. What is a shadal? Well, a shadal is a chunk, we call a shaded element, which is a chunk of something that's shaded. And to do this, we broke into what we called 8x8 chunks of these shadals. Now, shadals roughly analogous to a texel. We chose 8x8 because it was small enough to not get significant overdraw, but big enough to run well on hardware groups. So it was sort of magic balancing act. I could see in the future a smaller chunk might be better, like maybe a 4x4 would be better in the future. It's something we didn't experiment with, but I could see that as hardware has more features in it and has different shading groups, that 4x4 might end up, in the end of the day, end up winning out. But 8x8 was a good compromise for now. And the objects are parameterized through one set of texture coordinates. This is basically the only requirement we have for an asset, that it needs a set of texture coordinates it can render to. It doesn't have to be a good set of texture coordinates, and we can do it automatically. And there's reasons that it work with even bad parameterization. Like we did some work on that, but more or less it just works that way. So it's sort of like texture space rendering, except the texture isn't real; it's fake. So the idea is that we have a very, very large virtualized space. It's huge. And what we do when an object comes on screen or changes its estimation, this is where the CPU comes in. We get an estimate for how big something could possibly be. So it's just a maximum bound, so we don't waste space in our virtualized space. Because there's no cost for something if it's not shaded. So we're just, as long as we can fit it in our space, we're fine. But we could run out if we don't manage it. So we do a very coarse estimation of something, and then we park it in there. And then the actual storage is stored in a virtualized, it's a very small amount of physical GPU memory. We needed about a 4K by 4K for 4K resolutions, which is 2 samples per pixel roughly, and that's the maximum bound that we felt like we needed. And what we did is we built a custom texture fetch, which uses virtualized storage system and performs the filtering. So effectively, the virtualized texture memory, it's like our own system, or is our own system, but at a very, very fine grain, not the very coarse grain that people have tried to use in hardware, support in hardware, because it's just too coarse to be useful. And we have a global shading bias. So if in the event that we started getting close to our fixed size buffer, we can bias effectively the filtering down. In our experience, doesn't happen very often. It can happen, but usually we're only using about half that space. But if it gets close to it, we'll just downsample in our experiences that in the cases where we could build that happened. users did not notice it. I think there's typically something very busy going on in the scene. This is a little too detailed to talk about much here, but we have effectively a multi-indirection table. Well, we have a base offset that points into the shader storage buffer, and then we have an occupancy bit field. And by counting the bits, so we can mark these bits when something's visible or not, right? By counting the bits, we can determine our offset inside the shadal storage buffer. So it ends up being 8 by 8 chunks of 8 by 8 shadal chunks. So yeah, it gets a little confusing. So then you have 64 by 64 shadals stored in effectively 2 entries into your base texture. So one base texture, but to store 64 pixels, there's only 2 values in there, and then so it's just point to the actual storage. There's some magic to do MIP calculations because there were some interesting things about how MIPs work with unordered axis views. So we manually implemented all the MIPs, and there's some complexity there to manage the borders and things. We have to clamp things, but I think that's a little mentioned in the paper. All right, so the first thing that happens in our scene is we have to figure out what's visible. And we do this what's called a marking pass. And the marking pass clears the bit fields of all the different possible things that could be seen. And then we render the scene after a ZPref pass. And then by using some hardware atomic operators and some cleverness, we're able to mark the actual bits that are used, would be used to do the visibility reconstruction. And, so it's down to a very fine grain, down to the different MIP levels that we're going to do. So we do a whole pass, and all it's doing is setting all the bits that we're going to render. And this is a little complicated, but again, it's in the paper, so you can read about it there. So once we have all the bits set, like we have these things, now we can take all this information, we're going to aggregate it. And what we have to do is a couple things. We have to build the actual rendering commands to submit to do the shading, but we also have to allocate the space. So when we do the marking pass, we haven't allocated anything yet. So we actually allocate our shadals every frame. So every single frame, we're allocating our virtualized space. It doesn't persist frame to frame. And there's a whole bunch of reasons that so the best thing to do is just throw it out and redo it. Part of what we do is we do this in parallel using some hashing functions so that we don't end up with serialization. And also timings on this in down the road a little bit. This ends up being pretty fast if you're very careful about it. And we end up with these buffers which contain a bunch of information about all the different shadal chunks we're going to end up that are visible and which need to be processed. We upload a little bit of data to the CPU so that we can determine how many shaders are used if we're running out of space and we need to bias everything. And also just for debugging purposes, it's useful to get data back. So once we've done all that aggregation, there's a lot of work that did go in the GPU. We're taking this aggregation, these buffers, and we're building out a bunch of command buffers to render the shadals and also the intermediate shading layers. And we use dispatch and direct to compute it. So what will happen is there'll be a bunch of entries that the CPU has no idea if something will or not be visible, but it puts an entry in there anyway, and it will reference and place in a buffer, and then the GPU commands will fill out what needs to be done. So you'll get entries in there having literally 0 entries because it turned out we submitted something for rendering, but nothing was actually visible. And so you actually get empty commands, and that's just perfectly normal part of our operation. And we could call these multiple times. We have multiple layers, which I'll talk a little bit about our multiple layerings. But effectively, the idea here is that the GPU everything stays on the GPU. So we're marking everything on the GPU, we're marking what's visible, we're aggregating the work, and the GPU is generating its own work. So finally, we get to the scene rendering. This is the simple part. This is like going back to DX8 level. A lot of the shaders, which could be anything, the material has a lot of freedom. It could complement the forward reconstruction with whatever it wanted. But the shaders are often very, very simple. They're just doing maybe a single equivalent texture fetch, just get the sample and then they just render onto the scene. Sometimes we composite UI together. So it's a really, really simple step, and then we can build the scene from that very simple step. We can also blend any forward objects. Some of our objects are forward rendered, not everything is decoupled, and we can mix and match right here. So we're effectively a superset of forward. So this decoupled implementation, you can just think of it as a superset of forward. Some interesting stuff in our material shaders. I could have a whole talk on this. It's very interesting because you have all sorts of stuff you don't have in normal materialing systems. You can get your previous sample if you want to save it. So you get exactly your previous sample. We use this for performance caching, but there's a lot of stuff you can do with it. You can get your previous layers. You can stack the layers and do some interesting operations on it. So there's a lot of stuff that you can do in our machine learning system that just which supported or which we were supported in our own custom language. It's one of the reasons why we invested in our own language, just because there was a lot of neat stuff that we needed to be able to do in a way that was friendly to tech artists. Uh, One of the things that happened when we started the project is originally some of our stuff, like our leaders, were forward rendered because we didn't think we would have time to do decoupled. But one thing that's happened is that, of course, the project, the artists wanted to do decoupled because we could do cool things automatically. Doing skin rendering is really easy because you can store as many layers as you want, store the data, and then access them from the next layer. So you can do Gaussian blurs on skin, which is real common intrinsically. There's no special thing we have to do to implement it. It's just a property of our material system. You can compute normals dynamically from height maps, all this stuff. It's just a fallout of the way our system works. So here's an example of Sappho work in progress where we use the material system to do the skin. So that ended up being an interesting benefit for it that the artists really started embracing. And it's at the point now where we can't even render with a forward render without making a fallback because the materials have a dependency on needing previous layer evaluation. Now I'm going to run a little demo or a video of a demo, a video in a video. And this is an asset we took that's in Ashes. And here I'm just moving around. You can actually see it dynamically showing you what has been processed and what's not. And you can notice that the hidden surface removal, and you can see the shadal chunk boundaries. You can also notice is that as you're moving through the MIP, different things are visible because some parts are visible at different detail levels than others. And it's all dynamically blending between all these different subsections at a very fine grain. And that blue-green map is a map of what's actually visible and what's not, or what's partially visible and what's not. The shadals themselves are stored in this buffer. So here's what the buffer looks like. It looks like scrambling every frame because, as I said, we really reallocated every frame. And it's not deterministic. One frame to the next frame can have a different layout for storage space, which is what you would expect when you're dynamically allocating something in parallel in the GPU. So there's more of this in the paper, but what we couldn't do is do a tool frame analysis between a forward and a decouple, just because we can't implement the entire game. But what we can do is, because we're a superset of forward rendering, or mostly a forward renderer that sort of does the shading ahead of time, you can figure out like what performance were you paying that you wouldn't have paid if you did it forward. So we end up being able to get a good idea of like how much overhead you're actually paying for the decoupled renderer. And there's some caveats here which are talked about in the paper, but our estimate is that we're paying about 10%. Maybe as high as 15%. It's a little bit tricky because the shading samples don't match up one-to-one, as talked about in the paper. Yeah, so it's just pretty good. One of the things is we think there's some issue with our current NVIDIA solution, so I'll take these times with a grain of salt. 1600 was much faster, to the point where shading is only taking 25 or 30% of the frame. So at that rate, like, we're obviously able to shade very quickly, which gets into why we don't reuse samples, because when you're at 30% shading, you're not going to gain a lot of performance by reusing shading across frames. So the kind of conclusion here is that shading, decoupled shading works, and is minimal overhead. So this is intended to be a reference for other solutions. So this solution will work for almost any case, and we really wanted to let people know that this is how you can implement something, and you can only get better from here, and it is competitive. And there's some details in the paper about it. So there's some future work here, but I'd like to just leave some time for some running late for questions, and you can read the paper for some more details.